Okay, so here we're going to work through this problem here. So it says you want to make a open top box from a 10-inch by 12-inch piece of cardboard by cutting out squares from each corner and folding the flaps up. How can we maximize volume of such box? Okay, so here, so think of, we have this piece of cardboard, right, and I'm going to cut out squares of each corner, right? So I'm going to cut out from each corner square. So I don't know how big my squares are going to be. Right, I just know that in each corner, I'm going to cut out the exact same square. And then fold it up and make some kind of box, right? So here, so it'll look something like this. All right, and here it's up to me to decide how big should these cutouts be. All right, do I want something like this, or I want as wide as I can get, or do I want to kind of go for some box like this? Does it even matter? Will I get the same volume here? Excuse, God, that's bad. Yeah, let's try that again. Okay, so something like this. So what would be the best approach, right? Okay, so for these types of problems now, if you ever unfolded a box, you'll see it's a bit more complicated than this, but it's a nice kind of starting point to simplify the type of problem, to see how we start off with just like a piece of cardboard, and what effect cutting out the corners and then folding it up, what effect the volume has on the volume of creating such a box, right? And what we'll see is that it is going to matter, right, how we cut these corners in order to maximize the volume. Right, and we want to determine when would that max volume happen. Okay, so first let's see here. All right, so if we have something like this, we said what this was 12 inches, and this is 10 inches. Okay, and the volume of such it's essentially a rectangular prism, right? If you see the box, the volume of this box will always be of a figure like this. The volume would be length times width times height, right? Where if we think of the height as the flaps being folded up, the height will always be our, whatever this value of x is, right? Because these are the flaps that we fold up. So that's always going to be our height, right? Our length and our width is whatever is kind of left over here, right? It's the base here. So the length here is always going to be this portion here, which is not 12, right? Because I've removed 2x, right? The 2x comes from this corner here, right? And then this corner here, right? Those lengths. Right, I cut out an x on each side, right? So that'll be 12 minus 2x, and then here, right, same kind of approach here. The length here is going to be not 10, that's too much, because I've cut out 2x. All right, okay, and height is always x, right? So h will always be x. Okay, so I think I have everything I need here to connect my volume, right? Volume is going to be length times width times height, and we said that that would be 10 minus 2x, 12 minus 2x, and then the height, which was x, right? The size of the flap. Okay, all right. And so now let's do a little simplification, right? So now here I have an equation that's strictly in terms of x, right? And x is the length of the of the flat that I'm cutting out, right? So I found a way to relate the volume with how much I'm cutting out of each corner there. So here, if we do this, what do we get? 10 times 12 is 120. 10 times a negative 2 is negative 20. Negative 20x, excuse me. Negative 2x times 12x is negative 24x. And then lastly, we have plus 4x squared. And then times x here. So let me distribute the x, and if we combine like terms here in the middle, those two middle terms, so we get 120x, and then minus 44x squared, and then lastly plus 4x cubed. Okay, and this gives me the volume of the box, right? Again, I don't know how big x is going to be. Now, if we were in a calculus course, we would develop calculus techniques to help us solve this, right? But here, we don't have those tools yet developed yet. So all we can do here is really just graph this equation. All right, so I'm going to go ahead and pull up Desmos here. All right, and I'll graph 120x minus 44x. X plus 4x cubed. All right. Okay, so here, let's adjust here. So we're not really seeing it. So let's see. Let's go y to go negative 2. And is that enough? Oh, excuse me. I thought that looked weird. Okay. All right, there we go. Okay, that's a little better here. Okay, so now let's adjust the window here, just so we get something that is, I can suss out the details from the graph here. All right, so let's restrict. We don't need to go all the way to 14. We can just go, let's just stop it at 8. And actually, let's do. Okay. All right, and then along the y as well, just go to 2. All right. Okay, so what we see here, remember, let's kind of put some restrictions on our function f of x, because it doesn't make sense to take into account all numbers. First of all, we can't cut out a negative length, so there's definitely a lower bound. So x needs to be bigger than 0, and there's also an upper bound here, right? Because if you look here, right, there's only so much I can cut out here, right? If we're cutting out x here, then really 5, and you could tell that when I cut out 5, well, really then I can just fold the paper in half, and I don't have much of a box, which is, which you can tell from here, right? Remember, the input, the value for x, 5, is how much you cut out. And then the output is the volume, right? So this f of x is representing the volume. Okay, so really it doesn't make sense here for it to be anywhere bigger than 5. All right, those are really what my actual domain needs to be. Okay, so we can't cut x to be larger than 5, because then it goes beyond the limits of the size of my cardboard here. All right, and So now we could say here, all right, so a really small one, a really small flap, right, or a really wide box doesn't really make sense in terms of maximizing volume, right? But also doesn't make sense to have a really tall one, right? This is a really tall one. I get a really small volume. So there seems to be a kind of a sweet spot here, and we can see it here, right? That is kind of the maximum of the function, right? But the maximum of this particular function is representative of the volume. So the max function gives us the max volume, right? And that corresponds to this 1.811 to be how much you should cut out, right? So in other words, the height of the box. Should be 1.81 inches. Now in doing that, I will have optimized the amount of volume, how much it can hold. And that's what this second number represents, right? The output, right? The range. That's what the 96.7, and that would be the units there would be cubic inches, right? And you can tell from your formula, right? The highest power is cubic, right? So it would be in cubic inches, right? So that is how we determine how to maximize our volume, right? And like I had mentioned earlier in the video, right? This is kind of to kind of introduce us to this idea of just kind of maximizing given certain restricts, right? Which is a topic that we covered in calculus, and we'll develop some more advanced techniques. But here, this technique is what we'll use to determine some kind of a maximum here.